Chapter 11, our last chapter. We look at 11.1, vectors and the geometry of space. And your objectives in this lesson: we write the component form of a vector, we perform vector operations and interpret the results geometrically. We're going to do that today in this lesson probably. Write a vector as a linear combination of standard unit vectors, and also to use vectors to solve problems in using force or velocity. These are real nice applications that we're going to see. First of all, what is a vector? So we have to kind of look at that. And a vector is basically a directed line segment. You can read this piece right up ahead, that's important, but it's a line segment, and you can see one right here. Now it looks a little bit like it's a ray, or it looks a little bit like it's a line segment with an arrow in it, and that's more what it is. The arrow just tells us the direction that it's going, so we call it a directed line segment. It is a beginning point and an ending point. The beginning point we call the initial point. Its terminal point is the final spot. It stops there, it doesn't keep going. So when you see these arrows down here, that's where it stops. We're not going to put a dot at the end, or either end, but this is where the vector stops, so please be aware of that. So anyway, this directed line segment PQ has an initial point, terminal point, and length or magnitude. Now that is denoted with the use of the double bars here. We call that the magnitude of PQ, and we'll talk a lot about that in this chapter. Directed line segments that have the same length and direction are all equivalent. Imagine a group of arrows, if you would. These are all the same length, they are all the same direction, and so these are equivalent even though they're not in the same spot. Okay? Alright, let V be represented by a directed line segment, and let's see, I think I need to go back a section. Yes, I do. Alright, the component form of a vector is a vector in the plane, and we denote it with this bold-faced V, but most of you don't have the capacity to write that bold-faced V, and so what we typically do is use what's down here. We use a U with an arrow on top, or V or W, and that indicates that we're talking about a vector. Some people do this, they'll write it like that to indicate it's a vector. I probably do that more than to show it's a vector and not a ray. So you might want to think about going which route you want to go there, but you'll see this from me. Okay, it's hard to do the boldface unless we're printing, and so your textbook will use this. When we're writing, we use it this way, or you could use that way as well. Alright, let's go back to this page. We've got two vectors, our directed line segments, PQ going from 0, 0 to 3, 2, and RS going from 1, 2 to 4, 4. And we want to show that they're equivalent. Now if I slide back a page, we can say they're equivalent by having the same length and direction. Well, the length was simply, we're going to use the distance formula. So if I say the distance, this is going to be from, this is PQ. It's going to be 3 minus 0 quantity squared. Plus, and then I've got 2 minus 0 quantity squared, and of course we know what those are, and I just want you to see what we're doing. So that will equal the square root of 13. RS, on the other hand, and of course I should be labeling this correctly. Let me go back and do that up above. Is equal to, well, it's 4 minus 1, which we know is 3. So that distance squared, that's a 2. Squared plus 2 squared is the distance on the y. Is also the square root of 13. Okay, so that looks reasonable. Now it also said they had to have the same direction. Now how would I find direction of these? Well, I think I could just simply look at their slope, right? The same steepness would give me the same slope. So I'm going to look at the slope of PQ. So I'm just going to say the slope of PQ is the rise, which is 2 units, over the run, which is 3 units, which is 2/3. And the slope of RS we see here, the rise is also 2, the run is also 3, it's 2/3. Okay, so we can say they're equivalent, those two parts are the same. Alright, well, oftentimes it's much more convenient for us to say, hey, let's not just put these vectors all over the place, let's have them in something in what's called standard position, which means their initial point is at the origin, and the terminal point can be anywhere or in the plane, but we want the initial point at the origin. Okay, so that's going to look like this. This is in standard position. Obviously the vector right here, v, is in standard position, u is not. If v is a vector in the plane whose initial point is the origin and whose terminal point, v1, v2, then the component form of this is just simply given by that. So now remember, this is a little different. Notice the different notation that indicates it's a vector in standard form. So one of the points, the initial point is 0, 0, and this would be its terminal point. So that's an important point to notice. The 0 vector is denoted by bold 0, which is in component form would be 0, 0. So this is called component form when it has, they're not parentheses, I don't actually know their name, but it has this kind of bracketing on it. Okay. The definition applies two vectors can only be equal if and only if each of their components are equal. So u1 has to equal v1 here, and u2 has to equal v2. So how do we convert this? Well, we simply take the terminal point minus the initial point and come up with v1. So v1 here is equal to q1 minus p1, and q2, or this v2 here, is equal to q2 minus p2, what we'd consider the difference of the x's and the difference of the y coordinates. Okay, the distance formula, you see that the magnitude is simply the square root of v1 squared plus v2 squared. So we've simplified it a little bit. Sometimes we're going to be given the points, sometimes we're going to be given the components. So that's important to know the difference. All right. If we have this vector v, it can be represented by this directed line segment in the standard position. Its norm, the length of v is called the norm. All right. Okay. So if the norm of the vector is equal to 1, we call it a unit vector, and we're going to speak a lot about unit vectors. And if the norm of the vector is 0, it's called the 0 vector. Doesn't seem to have a lot of interest for us. The other one has a lot more interest. Okay. Definitions of vector addition and scalar multiplication. Now I didn't talk about it, but scalar is just simply a number that goes out front. A vector has two components. Scalar is just a number that we're multiplying by it, and you can see that happening here. These are pretty straightforward. I can give you examples, but I think you can work through them pretty quickly. Okay. What's more interesting, I think, for us here is to look at this and say, geometrically, the scalar multiple of a vector is the absolute value of c times as long as the vector. And you'll notice if I have here's vector v, if I multiply it by 1/2, its length is obviously 1/2 as long. Okay. And here it's twice as long. But if c is negative, I get the opposite direction. So instead of v going from here to here, now the opposite of v it's just like we're switching terminal and initial positions. Okay, and so that's an important piece that you need to recognize. We can add the two vectors together as well. Here's vector u and vector v. And so what we typically do is we'll say, to add them, we're going to move, if you would, this vector v, we're going to draw it at the, if I could draw it more straight, that'd be great. We're going to draw that vector right on the end of the other vector. And then u plus v is this vector right here, which you can see right in here. Now the same thing could be hold true. We could say I took v and then added u to it, and you'd see we'd get the same vector in a different spot, but exactly the same vector. Remember, they're equivalent vectors if they have the same direction and the same magnitude. And so you can see that happening both ways. We call that the resultant vector, and it's always going to be the diagonal of a parallelogram with u and v as its adjacent sides, whether they're on the top here or they're on the bottom that you see right here. Okay, and below we see this equivalence. We've got a vector addition here. We've got it, in this case, it's hard for me to see that. We're simply taking the scalar multiplication this time. We're taking a vector u and multiplying it by k, and now that vector has become longer. Here we're doing subtraction, which is take the first vector and add the opposite. And so it's a little more confusing. This one's a little less intuitive than the other one, I think. But remember, we're add u plus or u minus v is equal to u plus the opposite of v, and that's what you're seeing here. Here's u, here's v. The opposite of each of those are going the other way, and so that's what you can see, u plus the opposite of v. And the direction matters here, so remember that. All right, we're going to call that a day for right now. We can pick this up next time. Okay, I kind of lied to you there, I'm afraid. I want you to look at these examples up here. I think you'll be able to do them pretty quickly, straightforward on your own. If you need some help, come talk to me. We'll work through it, but these are pretty straightforward.